So in the previous lecture, you learned about quantum mechanical model, and that quantum mechanical model is a lot more advanced compared to the Bohr's model of the atom, because this model can explain the behavior of electrons and so much more in comparison to the Bohr's model. And so in this chapter, you learn about energy levels, right? That within an atom, you have energy levels, and within energy levels there are sublevels, and then each sublevel contains orbitals, and the orbitals are basically where electrons can be found, right? So it's a mathematical representation of where the electrons could be found. So the larger the orbital, the higher the probability of finding an electron. So for example, we have sublevels S, P, D, and F. Right, so you have an S sublevel, a P sublevel, D sublevel, and F sublevel. But then you also have the orbitals that exist in these sublevels. So in an S sublevel, you have S orbitals. In a P sublevel, you have the P orbitals, and so on. And it's in these orbitals that the electrons reside. So in this third part of the chapter, you're going to learn more about the orbitals and how the electrons are arranged in these orbitals. So the first concept that you're going to learn here is called the electron configuration. So this basically tells you how electrons occupy the orbitals. And by definition, electron configuration shows you the specific orbitals that electrons occupy for an atom. So you can think of electron configuration like an address. So the electrons live in a specific address. It's kind of like their home. So for example, if we look at a hydrogen atom, we know that a hydrogen contains a single electron. And so a hydrogen atom in its ground state tells you that we have a hydrogen atom in its lowest energy state, meaning that that electron is at the lowest energy level. Because sometimes you can input energy, right? You can have the electron absorb energy and then it goes to a higher energy level they call the excited state. And so let's just assume that we have a hydrogen atom in its ground state. What would be the electron configuration? So when you look over here, we have hydrogen. This is the symbol for hydrogen. And this thing right here is its electron configuration. So how did we get this? What is this electron configuration exactly? So the first number up front, which is, I guess you can call it a coefficient, is the principal energy level or the main energy level. So if you can visualize Bohr's model of the atom, it's the first stationary state, right? It's the first energy level when it says energy level 1. Okay? And this letter right here, letter S, is basically the sublevel. Remember that you have 4 different sublevels. You have S, P, D, and F. So it tells you that the first electron, okay, or the only electron of the hydrogen, is in the S sublevel. And of course, an S sublevel contains orbitals. So you have an S orbital in an S sublevel. So the superscript, okay, or the exponent, contains or tells you the number of electrons in that specific sublevel or orbital. Okay, so in this case, because we only have 1 electron for a hydrogen, then we put a number 1 up top, okay, as the exponent or the superscript. So this is the electron configuration for a hydrogen atom. And you always have to remember that an electron configuration always begins with a 1s, because 1 is the first energy level. Electrons reside in the first energy level, which is the lowest energy level. So let's look at a second atom here, helium, right? So we know that helium contains 2 electrons because the atomic number is 2. So helium, this is the symbol for helium, and this is the electronic configuration for this element. And so again, in its ground state, you have 2 electrons. So we have the first energy level, and then within the first energy level, you have the sublevel. And in the sublevel, you have the orbitals. In this case, you have an s orbital. And then within the orbital, you have a total of 2 electrons. So, so now we have placed all of the electrons that helium has. So this is the electron configuration of the atom helium. So 1s2. And again, there's a reminder here that you always have to remember that orbitals, energy levels, and sublevels can hold a certain max number of electrons, right? So each orbital can hold a maximum of 2 electrons, but because you have multiple orbitals in sublevels P, D, and F, they can have more than 2 electrons. So for example, the P sublevel contains 3 orbitals, and so multiply that by 2 electrons, so you have a total of 6 in the P sublevel. And the D, you have a maximum of 10 electrons, and an F sublevel contains a maximum of 14 electrons. And this right here basically summarizes all of that. So these are all your sublevels. So you have an S sublevel, which holds a maximum of 2 electrons, a P sublevel, 6 electrons, and so on. And so whenever you're writing the electron configuration, again, you put the number of electrons as a superscript or an exponent. So here, if you have a maximum of 2 electrons, you would put S to the second power, or S2, and then P6, D10, F14. So we just looked at the electron configuration for the first 2 elements in the periodic table, hydrogen and helium. Now we're going to look at the electron configuration for multi-electron atoms containing more than 2 electrons. Okay, so that's basically the rest of the elements in the periodic table. And so whenever you're writing electron configuration for elements containing more than 2 electrons, it's actually a little bit more complicated. Orbitals are filled with electrons based on their overall energy, right, from lowest to highest energy level. It's kind of like a bucket of water, right? Let's say we have a bucket and you're trying to fill it with water. Whenever you're filling it with water, water goes at the very bottom of the bucket, right? And it's uniformly distributed on the surface, and then it gets filled up. So whenever you're filling the orbitals with electrons, we use the same concept, okay? But in terms of energy levels. And so we fill the orbitals with electrons in terms of increasing energy level. So again, if you can visualize Bohr's model of the atom, you have the nucleus and then you have the orbits, or the stationary states. But again, we're switching to the more appropriate terminology here. Energy levels. So these orbits are now called energy levels. So the first energy level is lower in energy compared to energy level 2. And then you have, let's say, energy level 4 is greater in energy compared to energy levels 3, 2, or 1. And so the higher the n value, the greater the energy. So let's say that we have these specific energy sublevels. So we have a 3s, a 2s, and a 1s. Right, so they contain the same type of sublevel, S sublevel, but their energy levels are different. Right, so you have energy level 3, energy level 2, energy level 1. So this tells you that you have an S sublevel in energy level 3, you have an S sublevel in energy level 2, and an S sublevel in energy level 1. So in terms of overall energy, the 3s sublevel has greater amount of energy compared to 2s, and the 2s has greater amount of energy compared to the 1s. And then in terms of, let's say, the same energy level, right? We have energy level 3, and then we're comparing the sublevels D, P, and S. So when it comes to this, you have a 3D, a D sublevel in energy level 3. This would contain a greater amount of energy than a 3P, and a 3P has a greater amount of energy than a 3S. So the S among the sublevels, the S sublevel has the least amount of energy, and then the F sublevel has the greatest amount of energy because it contains more electrons. And whenever we're writing the electron configuration for the elements, we use this principle called the Aufbau principle, which is basically the German word for building up. So the Aufbau principle is used systematically to build up the electron configurations for the elements. And so it's if you're not completely familiar with writing out the electron configurations, it's a good idea to follow this, because this is the most basic way to write the electron configuration for any elements in the periodic table. So you can think of it in terms of energy levels and sublevels. So you can make this diagram shown here on the right corner. You can have the first energy level here, so energy level 1, energy level 2, energy level 3, 4, 5, 6, and so on. And then within an energy level, you have a sublevel, an energy sublevel, right? So if you remember from the second part of chapter 4, that each energy level can contain a maximum number of sublevel. So if you have energy level 1, you have one sublevel. If you have energy level 2, you have two sublevels. So the energy level basically matches the number of sublevels. So, and that's why when you're writing this diagram, you only have one sublevel in this energy level. You have two sublevels in energy level 2, the 2s and the 2p sublevels. And then for energy level 3, you have three sublevels, the 3s, 3p, and 3d. So this tells you that a 3f doesn't exist in this energy level. Same thing in energy level 2, that a 2d or a 2f don't exist in this energy level. Okay, so you have to follow this building up concept. So again, if you have energy level 4, that means you have 4 sublevels, 1, 2, 3, and 4. And then 5 sublevels, 5s, 5p, 5d, 5f. That means you also have a 5g. So anything beyond f, the next sublevels are basically the next letter in the alphabet. So you have S, P, D, F, and then G, H, I, so on and so forth. Okay? So that's basically the first step in learning how to write electron configuration, is to remember this diagram here. So you can treat this like your map, right, to determine the address of the electrons. So the sublevels, or the orbitals within the sublevels, are filled with electrons in this pattern, in this order. Okay, so you have a 1s, which is the lowest energy level. So the electrons go in the 1s first before going to the 2s. So you have to completely fill the 1s before moving on to the next one, the 2s, and then you go to the 2p, the 3s, 3p, 4s, 3d, 4p, 5s, in this order. So the orbitals are filled with electrons in this specific order. All right, let's look at a few examples here. And lithium, for example, we have 3 electrons. So we have 3 electrons to distribute, right? So we're going to distribute them in the energy sublevels. So again, we're going to fill the 1s first completely. And so you know that the 1s can only hold a maximum of 2 electrons. The s sublevel can hold a maximum of 2 electrons. And so because we have a total of 3, 2 of them will go on the 1s, okay, and the remaining 1 electron goes in the 2s. So we have 2 in the 1s and 1 in the 2s, a total of 3 electrons. So we've basically just distributed a total of 3 electrons in the sublevels. Okay, so this is the electron configuration for lithium. And then we move on to boron, and boron has a total of 5 electrons. And so we're going to do the same thing here. We're going to fill the 1s first, and then the 2s, and then move on to the 2p. So 1s, 2s, and 2p. 2 of the electrons will go in the 1s. Another 2 electrons maximum will go on the 2s. And then the remaining number of electrons in the 2p. So we have 1s2, 2s2, 2p1. Again, a total of 5 electrons. Looking at nitrogen, nitrogen has a total of 7 electrons. So we're going to do the same thing here. Again, starting from the 1s, and then the 2s, the 2p, 3s. And so because we have 7 electrons, 2 of them will reside in the 1s, another 2 will go in the 2s, and then the remaining 3 will go in the 2p. So remember that a p sublevel can hold a maximum of 6 electrons. Okay, so the p sublevel contains 3 orbitals, and the 3 orbitals, and each orbital contains a maximum of 2. So 3 times 2 gives you 6 electrons in the sublevel. All right, so this is the electron configuration for the nitrogen. And then finally we have scandium. So this is a slightly larger element. So we have 21 electrons because the scandium is number 21. Its atomic number is 21. And so we're going to start off with 1s again from the very bottom, right? The lowest energy level, 1s, and then 2s, 2p, 3s, 3p, 4s, and all the way to 3d. So you can always start with 1s first if you like, and then move on from there until you have completely distributed all 21 electrons. So we have 1s2 because an s can hold a maximum of 2. So you can just distribute 2 electrons for each s sublevel because that's their maximum. Right? So we have 1s2, 2s2, 2p6 because again a p sublevel can hold a maximum of 6, and then back to 3s2, 3p6, 4s2, 3d1. And remember that a d sublevel can hold a maximum of 10 electrons. So when you add up all the when you add up all the exponents or the superscripts, the numbers in red here, that should add up to 21 electrons. So that's how you know that you've distributed all 21 electrons. And again, you can always double check the order of the sublevels by consulting this diagram. So again, you start off with 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So let's introduce a new concept here called electron spin. So an electron has a specific spin, and it's their basically fundamental property. So an electron spin is a fundamental property of all electrons that affects the number of electrons allowed in a specific orbital. So there's a reason why there's only a maximum of 2 electrons allowed in an orbital. And the reason why is because of the electron spin. And there are 2 different spins for an electron. And one spin is going up. Okay, so one electron is spinning up, and the other electron is spinning down. And so they're given a specific numerical value. If you have an electron that's spinning up, then it's a positive 1/2. And then if you have an electron spinning down, they're given a negative 1/2. And they typically give this symbol m sub s, but you don't need to know that information because it's a little bit more advanced. So the only thing that you need to know here is the fact that an electron has 2 different spins. One is spinning up and the other one is spinning down. And so they're given a symbol. So an electron that's spinning up is given this symbol here, which is basically a half arrow. Okay, so this is spinning up, and the other electron spin is spinning down. So you have a half arrow pointing down. So for example, if we look at helium, helium has 2 electrons that reside in the same orbital, right? So you have an s sublevel, and an s sublevel contains only 1 orbital, and that would be the s orbital. And so you have 2 electrons that reside in the same orbital, the s orbital. And so this element contains 2 electrons, and each electron has a different spin. One is going to be spinning up, and the other one is going to be spinning down. So the concept of electron spin is important whenever we're learning this new concept called the orbital diagram. And orbital diagram is basically similar to an electron configuration. It's just another way to show an electron configuration for specific elements. So by definition, an orbital diagram gives similar information as electron configuration, but symbolizes the electron as an arrow, a half arrow, and the orbitals as a box. So let's look at Hund's rule really quickly. So Hund's rule basically states that electrons must occupy all the orbitals of a given sublevel singly first before pairing begins. So what that means is that if you have, let's say, a p sublevel, and you know that a p sublevel contains 3 different orbitals. Okay, so you learned that in the previous lecture. So if you have a p orbital or 3 different p orbitals in a p sublevel, that means you have a px, py, and pz. Right? Same thing with the d sublevel. D sublevel contains 5 different d orbitals. So what Hund's rule is saying is that before you fill an orbital completely, first you have to distribute the electrons evenly among the 3 orbitals in a, let's say, p sublevel. So let's look at a few examples here and look at the difference between an electron configuration and an orbital diagram. But they're very similar. The only difference is, again, the electrons themselves are represented by half arrows, and then the orbitals themselves are represented by boxes or lines. So let's take a look at a few examples here. So hydrogen, we have hydrogen, lithium, neon, phosphorus, and scandium. So these are the same elements that we looked at as examples for electron configuration. So you should already know the electron configurations, right? So for hydrogen, it's 1s1, right? Because it has 1 electron. And then for lithium, you have a total of 3 electrons. So 2 plus 1 equals 3. And then for neon, a total of 10. 2 plus 2 plus 6 equals 10. And this is the order of the building up or filling up the sublevels. So how would we draw the orbital diagrams for each element? So when you look at hydrogen here, for example, hydrogen only has 1 sublevel, right? So you have 1s. And an s sublevel contains 1 orbital, the s orbital. So this is what the orbital diagram would look like for hydrogen. So you have a box containing 1 electron that's spinning up. Okay, so now let's look at lithium. Lithium would have 1 box for 1s and then another box for a 2s. So the first box basically contains 2 electrons, and so you would put 1 electron that's spinning up and then another electron that's spinning down. And then we do the same thing for the 2s. You have 1 electron in that 2s, so you put 1 electron that's spinning up in this box. So this is the orbital diagram for lithium. Now let's move on to neon. So neon has the 1s box, the 2s box, and then the 2p. The 2p contains 3 boxes that are connected because of the fact that a p sublevel contains 3 different p orbitals. So each box represents an orbital, a p orbital. So you have a px, py, and a pz. All right, so how would we fill these boxes with electrons? Well, according to Hund's rule, electrons must occupy all the orbitals of a given sublevel singly with 1 electron first before pairing begins. And so we can do the same thing for 1s and 2s as we did for the previous examples. So you have 2 electrons here, or a pair of electrons, one spinning up and the other one spinning down. Same thing for the 2s. And then when it comes to the 2p, you would fill the boxes singly first. Okay, so you put 1 electron here, another electron on the second box, and a third electron on the third box, and then you start over at the very beginning to start pairing them up. Okay, so now you would have something like that. So that's how you would fill the orbitals using Hund's rule. All right, let's look at phosphorus really quickly. So phosphorus contains a 3p that's that contains 3 electrons. So it would look something like this. So you have a 1s2, 2s2, 2p6, 3s2, and a 3p3. Right? So instead of putting another electron here first, you have to spread them out evenly among the orbitals, the p orbitals. And the last one here is for scandium. Again, I skipped all of this step because it's basically similar to the phosphorus, the first 1, 2, 3, 4, 5, 6 boxes. And then you move on to the 3p, right? So 3p contains 6 electrons. So you have 2, 4, 6, and then 4s, 2 electrons, and then 1 in the 3d. So the 3d contains 5 boxes because a 3d sublevel contains 5 orbitals. And so that means that an F sublevel would contain 7 boxes because of 7 orbitals. Alright, so let's look at a few examples here. Again, if you want to try them out yourself, you can always pause this video. Write the electron configuration and orbital diagram for the following elements. So we have all these examples here. We have beryllium, silicon, argon, titanium, germanium, and krypton. And so you would need a periodic table here so that you can determine how many electrons there are for each element. So for beryllium, the number of electrons is 4. And so you have 4 electrons to distribute total. And you can always follow this diagram here, the Aufbau diagram. So you can fill the 1s first, followed by the 2s. So we're going to write out 1s and 2s, and then distribute the 4 electrons. So you're going to put 2 in the 1s, and then another 2 in the 2s. Because again, the maximum number of electrons that an s sublevel can hold is 2 electrons. And then for the orbital diagram, you would have 1 box for each sublevel. So you have 1s sublevel and a 2s sublevel. So you have 1 box for each one. Okay, and then you're going to put 2 electrons in each box. So 1 spinning up and the other electron spinning down for a total of 4 electrons. So silicon in the periodic table is number 14, and so it has a total of 14 electrons. And so now we have a total of 14 electrons to distribute. And so you would start off with 1s, and then 2s, 2p, 3s, 3p, 4s, and then start filling with electrons until you run out of electrons to fill. All right, so that would be 1s2, 2s2, 2p6, 3s2, 3p2. So again, when you add up all the electrons, the number of electrons, that should equal 14 electrons. So in terms of the orbital diagram, you have 1 box for a 1s, another box for the 2s, and then 3 boxes for the 2p and 3p. All right, so as you can see here, the 3p, we distributed the 2 electrons evenly among the boxes, right? So you put 1 for each box instead of pairing them up right away. According to Hund's rule, you have to distribute them evenly among the orbitals. Now, argon is number 18, and so this is the electron configuration for argon. And for the orbital diagram, it's basically similar to the first 1, 2, 3, 4, 5, 6 boxes for silicon, and then a completely filled 3p sublevel. So that means you have a total of 6 when we say completely filled. All right, for titanium, in the periodic table, titanium is number 22. So it contains 22 electrons. And a lot of the transition metals, they contain the d orbitals. Okay, so titanium will contain a 3d orbital. So as you can see here, the last one is 3d. So you have a 1s2, 2s2, 2p6, all the way to 3d2. Remember, notice that the 4s comes first before the 3d. So that tells you that the 4s is actually lower in energy than the 3d, even though the energy level is higher than the 3D. And the reason why is because these sublevels, they also contain specific energy. So when you add them all up, the overall energy of the 3D is greater than the overall energy of the 4s. So, and you can also see that here, the 4s comes first before the 3D. All right, so then we can draw the orbital diagram. So again, it would be, so all the way to 3p6, that's basically similar to argon, right? 3p6 all the way here. And we're just basically adding 4s and the 3D. So here's the 4s and the 3D. And here's the answer for the rest of the elements. So far we've looked at two different concepts. The first one is electron configuration, and then the second one is orbital diagram. The third concept that I want to show you here is noble gas electron configuration, which is supposed to be a shortcut for writing out electron configurations. So by definition, a noble gas electron configuration is the shorthand notation for writing out electron configurations. So for example, here we have sodium. So when you're writing the electron configuration, the full complete electron configuration, it's 1s2, 2s2, 2p6, 3s1. So that means that sodium has a total of 11 electrons, right? So you have 2, 4, plus 6 is 10, plus 1 is 11. So you have a total of 11 electrons for sodium. And this is what the normal electron configuration looks like. Now, what does it mean by noble gas electron configuration? Well, what that means is that we're using the noble gas as our starting point. So when you look at the first three sublevels here, the 1s, the 2s, and the 2p, when you count the total number of electrons, you have 2, 4, plus 6, a total of 10, right? So there's only one noble gas in the periodic table with 10 electrons, and that is neon. Okay, so neon has the same electron configuration as this, the 1s2, 2s2, and 2p6. This is the exact electron configuration for neon. So what we can do is to write out the neon sign, right? Neon symbol, followed by bracket or inside the brackets, and then the remaining sublevels or the rest of the electron configuration. So that would be symbol for neon and then 3s1. So this is the noble gas electron configuration for sodium. And you should always remember that whenever you're writing the noble gas electron configuration for a specific element, to always choose the preceding noble gas. Always choose the noble gas before that specific element. So in the periodic table, you have sodium, and the noble gas before that is neon. And so you're going to use neon as your starting point, your noble gas. All right, so let's look at a few more examples here for noble gas electron configurations. So we have beryllium, silicon, and titanium. And I've already given you the normal electron configuration here. How would you write the noble gas electron configuration for each element? So when you look at the periodic table, you find out what the preceding noble gas is, right? Find out what the noble gas is before beryllium. So in the periodic table, helium is the noble gas before beryllium. And so we're going to use that as our starting point. And we know that helium has 2 electrons. So that means that you can knock out the 1s2, right? The first 2 electrons. And then replace this with the symbol of helium. So we have helium followed by the rest of the electron configuration. So in this case, helium and then 2s2. And then we can do the same thing for silicon, right? So silicon, the noble gas before silicon is neon, right? And we know that neon has a total of 10 electrons in the periodic table. So knock out the first 3 sublevels here containing 10 electrons, and then write out the rest of the electron configuration. So the symbol followed by the rest, 3s2, 3p2. And then last one is titanium, and the preceding noble gas before titanium is argon. And so argon, we know, has a total of 18 electrons. Okay, so you have 2, 4, a total of 18. So you're going to knock out 18 electrons and then write out the rest of the electron configuration. So that would be 4s2 and 3d2. So symbol for argon, and then the rest, 4s2 and 3d2. So now we can use this concept regarding electron configuration to determine the total number of valence electrons per element in the periodic table. And valence electrons, by definition, are basically electrons that are involved in chemical reactions. So these are the outermost electrons. So valence electrons are electrons in the outermost principal energy level that are involved in chemical bonding or chemical reactions. And so when it says outermost principal energy level, that would be the highest S&P sublevels or subshells. So subshells and sublevels, they mean the same thing. So how do we determine the number of valence electrons per element? So you have to remember that elements in the same group, okay, so elements in the same group or vertical column have the same number of valence electrons. So for example, group 1 elements will have the same number of valence electrons. Group 2 elements, same thing. Group 3, 4, 5, 6, 7, and 8. So if they all are in the same, if you have 2 elements that are in the same group, they have the same number of valence electrons. So how do we prove that? So again, if you have, let's say, hydrogen, lithium, and sodium, these 3 elements will have the same number of valence electrons. Group 2 elements, same number of electrons, valence electrons, and so on. So looking at the first group of elements in the periodic table, we have hydrogen, lithium, and sodium. Let's write out their electron configurations. Okay, so for hydrogen, it's 1s1, right? Because hydrogen has 1 electron. For lithium, it's 1s2, 2s1. For sodium, it's 1s2, 2s2, 2p6, 3s1. So basically, the definition of valence electron here is the outermost principal energy level. So what that means is it's the highest S&P subshell or sublevels. Okay, so for hydrogen, the highest S&P sublevels would just be the 1s, right? And then you count the number of electrons that's in that 1s sublevel. So because we only have 1 electron in the 1s, hydrogen must have only 1 valence electron. And we can do the same thing for lithium. The highest S&P sublevel is the 2s, because we don't have a 2p. The 2p is empty. So you have 1 electron in the 2s, and then same thing for sodium, right? We have 1s2 all the way to 3s1. The 3s1 is the highest S sublevel, and so there's only 1 electron in that sublevel. So the number of valence electron then is 1 for sodium as well. So we know that a 3s is higher in energy because it's got principal energy level 3 or main energy level 3 versus energy level 2. Okay, so you always go with the highest S&P sublevels. So as a reminder here, the valence electrons are the electrons in the highest S&P subshells or S&P sublevels. So all of the elements in group 1 have 1 valence electron. So looking at these examples here, the number of valence electrons for the main group elements, so if you guys remember, the main group elements are the group A elements. All elements except for the transition elements are main group elements. So the number of valence electrons for the main group elements basically matches their group number. So group 1 elements will have 1 valence electron. Group 2 elements will have 2 valence electrons. Group 3 will have 3 valence electrons. And group 8 elements have 8 valence electrons. And we can look at this example here to kind of prove that concept. So if you have beryllium, for example, and magnesium, they're both in group 2 element. Group 2. They should have a total of 2 valence electrons. So when you look at the highest S and P sublevels, again the 2p is empty for beryllium and magnesium, and so the highest sublevel is the 2s, and you have 2 electrons in the 2s. And so group 2 elements will have a maximum of 2 valence electrons. And so the main point here in this slide is that the number of valence electrons matches the element's group number, with only one exception, which is helium, because we know that helium is a group 8 element because of the fact that it's a noble gas. But because helium only has 2 electrons, then the maximum number of valence electrons for helium is 2. So the next concept here is regarding core electrons. So if you have valence electrons, the outermost electrons, we also have the core electrons. And these are the electrons that are buried deep within the atom, and they're very difficult to access. It would require a lot of energy to access these core electrons compared to the valence electrons. So by definition, core electrons are all the electrons other than the valence electrons. And these are the electrons that are not involved in chemical reactions or chemical bonding. So here's an example. We have silicon. So silicon, when you look at the periodic table, it's in group 4, right? And so silicon has a total of 4 valence electrons. And silicon has a total of 14 electrons. 14 electrons. And 4 of them are valence electrons. So that means that silicon has a total of 10 core electrons. It's basically the remaining number of electrons. So if you have 14 total, and 4 of them are valence electrons, then 14 minus 4 equals 10 core electrons. All right, and you always want to remember that for the main group elements, the number of valence electrons matches the element's group number. So that's one way to easily determine how many valence electrons there are for a given element, at least for the main group elements. And then subtract that number of valence electrons from the total number of electrons to get the core electrons. All right, so let's look at a few examples here. How many core electrons are there for each element? So we have carbon, calcium, sulfur, and argon. So carbon, if you look at the periodic table, it's group 4, so it has 4 valence electrons. Calcium is group 2, and so it's got 2 valence electrons. Sulfur is group 6, it's got 6 valence electrons, and then argon is group 8, and so it has 8 valence electrons. Okay, so let's look at them one at a time. So carbon in the periodic table has the atomic number 6, and so it has 6 electrons total. And we determined that 4 of them are valence electrons because it's in group 4. And so 6 minus 4 gives us 2 electrons left. And so that's the number of core electrons. And then for calcium, it has 20 electrons, total of 20 electrons. And it has 2 valence electrons, so we're going to subtract 2 from 20. And so we have 18 electrons left, and those electrons are core electrons. And then sulfur has a total of 16 electrons, and 6 of them are valence electrons because it's in group 6. So 16 minus 6 gives us 10 core electrons. And then the last one here is argon, and it has a total of 18 electrons, and 8 of them are valence electrons, and so it also has 10 core electrons. So typically, for the noble gases, the number of core electrons matches the total number of electrons. But we also know that 8 of those electrons are considered valence electrons because they are the electrons that are on the outside of the structure of the atom, right? The outermost layer of the atom. And so So you can consider all of the electrons of the noble gases as core electrons because of the fact that they're very difficult to remove. It'll take a huge amount of energy to remove the electrons. Okay, so far you've learned three different ways on how to write electron configuration. The first one is the normal way, right? The normal technique where you have the Aufbau diagram, where you follow the Aufbau principle. So you distribute the electrons in the orbitals based on increasing energy level. So you have the 1s first, and then the 2s, and then the 2p, followed by 3s, and so on and so forth. The second way to do it is by using the noble gas electron configuration, which is sort of a shortcut, right? It's a shorthand notation in which you use a noble gas as your starting point. So you don't have to actually write out the entire electron configuration. You just pick a preceding noble gas, right? So as your starting point. So you have the noble gas prior or before the actual element. So for example, if you have sodium, in order to write out the noble gas electron configuration, you would pick neon as your starting point, followed by 3s1. The third way is using the orbital diagrams, right? So you learn how to draw orbital diagrams. Basically, it's essentially similar to an electron configuration, except you're using boxes as your orbitals, so you're using boxes as the orbitals, and then you're using arrows or half arrows to indicate what spin the electron has. So it could be spinning up or spinning down. Now, the last one that I'm going to show you is using orbital blocks in the periodic table, right? So you can just look at a periodic table and then be able to write the electron configuration by simply looking at a periodic table and knowing where the element is in the periodic table. In my opinion, this method is the easiest way to determine an element's electron configuration, because all you have to do is look at a periodic table, and depending on where the element is, you'll be able to write out the electron configuration. You can even use the noble gas electron configuration instead of looking at this diagram shown here on the left. Instead of using that, you can just, again, look at a periodic table. But again, it's up to you, whichever method you want to use in determining any element's electron configuration. But before you can use this orbital block method, you have to know what these orbital blocks are. And one of the requirements is to look at these blocks in the periodic table. So let's pretend that this is the periodic table here. So we have the transition metals here in the middle, and then we have these main group elements, and then also the lanthanide and actinide elements down here at the bottom of the periodic table. And so what are these orbital blocks exactly? Well, these are orbital blocks. Remember that there are 4 different types of orbitals. You have the s orbital, the p orbital, d orbital, and the f orbitals. Okay, so these orbital blocks are based off of those 4 types of orbitals. And so the first block here on the left is the s block, okay, s orbital block, and then the one in the middle is called the d block because they contain a bunch of d orbitals. And then the one on the right are called the p block, and then the one at the bottom is called the f block. Okay, so you have 4 different orbital blocks: the s, d, sp, d, and f. So the number of columns in each block is equal to the maximum number of electrons that can occupy the particular sublevel of that block. So for example, this S block right here contains 2 columns, right? You have group 1 and group 2. The P block contains a total of 6 columns, and you can count it. You have group 3, group 3A all the way to group 8A, the noble gases. So that's a total of 6 columns. And then when you count the number of columns for the D block, you have a total of 10. And then the F block, you have a total of 14. Okay, you can count that, you can double check it yourself. And so because the S block contains 2 columns, according to this statement here, the number of columns is equal to the maximum number of electrons that can occupy that particular sublevel. And so S contains 2 columns, so that means the maximum number of electrons is 2 electrons for that block. And then for the P block, 6 columns, so you have 6 electrons. The D block contains 10 columns, 10 electrons. And the F block contains 14 columns, and so you can have a total of 14 electrons maximum. And it sort of matches the rule regarding the maximum number of electrons that each of these sublevel can hold, right? So an S sublevel can hold 2 electrons, an F sublevel can hold a maximum of 14. And when you look at a periodic table, let's say this periodic table shown here, you have the row number in a periodic table equal to the number or n value of the highest occupied principal energy level. So basically, if you have row number 1, that means that the highest principal energy level that's occupied is the first energy level. So you have n equals 1, n equals 2 for the row number, for the second row number, n equals 3, 4, 5, and 6, and 7. And so these row numbers, or these n values, are basically the principal energy level. Okay, so we didn't really talk about principal quantum number, but this is basically what energy level is. So if you have principal quantum number 1, that means energy level 1. Okay. So let's look at this blank periodic table here again. So we have the S block, the D block, P block, and the F block. And so if we have an element, let's say the first column here, we have hydrogen, right? The highest energy level that it's occupied is the 1s, right? Because this is, again, the S block. And so the row number, the n value, is equivalent to the row number. So for a hydrogen atom, the highest energy level that it's occupied is the 1s. Okay, so if you have the element right below hydrogen, which is lithium, the highest energy level that it's occupied with an electron is the 2s, because lithium is on the second row in the S block. So that would be 2s. And you can do the same for sodium, 3s, and so on and so forth. So if you have beryllium, which is on the second row, S block, the highest energy level that it's occupied is also a 2s, similar to a lithium. Now, once you get into the D block, you subtract 1 from the row number. So that means that if you have scandium right over here, number 21, atomic number 21, scandium, the highest energy level that it's occupied is 3D, right? So scandium is on the 4th row. And so if n equals 4, you subtract 1, it becomes 3, right? So scandium has the 3D as its highest energy level that's occupied. So all the elements on the 4th row in the D block has 3D as their highest energy level. And then once you get back to the P block, the highest energy level that's occupied is equivalent to the row number plus the sublevel, okay, or the P block. So, for example, if we have carbon over here, carbon is on the second row, the highest level would be 2p. Okay, nitrogen, oxygen, fluorine, they're all on the second row, so the highest energy level that's occupied will be a 2p. And then once you hit the F block at the bottom, it becomes n minus 2. So that means that if your row number is 6, then you subtract 2 from 6, it becomes 4. So you have 4F, and then down below it is 5F, because 7 minus 2 is 5. All right, so let's look at an actual periodic table here and look at how we can use that technique to determine the electron configuration of any elements in the periodic table. So let's say, again, I'm just going to summarize it. So we have an S block here, we have a P block on the right, D block in the middle, and an F block at the bottom. And then we also have row numbers. You have row number 1, 2, 3, 4, 5, all the way to 7. And these elements here at the bottom, the lanthanides and the actinides are actually inserted here in this row, and that's why they have the same row number as cesium and barium for the lanthanides, and then the actinides have the same row number as francium and radium. Okay, so now let's say that we're trying to write the electron configuration for the simplest element in the periodic table, hydrogen. Right, so we know that hydrogen has one single electron, and we also know that hydrogen is on the first row in the s block. And so the electron configuration then is simply 1s, and then because it has one electron, we put 1s1. So that's the electron configuration of hydrogen. It's 1s1. And then for helium, we know that helium is right over here, but the reason why helium is on this side in group 8 is because of the fact that helium is a noble gas, and noble gases are very stable, and that's why they group them along with the rest of the noble gases. But in terms of number of electrons, helium should be right over here with the group 2 elements. Okay, and so because helium has 2 electrons, then it would still be on the first row and within the s block. So the electron configuration for helium is 1s2 because it's got 2 electrons. All right, what about for lithium? So once we get to lithium, that's 2s block, right? So that's 2s and then 2. So that means that that's the highest energy level that's occupied by lithium. So to build up the electron configuration, you would again start off with the 1, right? So you have 1s, 1s2, 2s1 for lithium. So you have to include the preceding electron configuration for lithium. So that would be 1s2 and then 2s1 for lithium. For beryllium, that would be 1s2, 2s2 for beryllium. And then once we get to boron, again, we're starting off with hydrogen again. So that would be 1s2, 2s2, and then this is the p block now, so it would be 2p1. Okay, and then we can do the same thing for carbon. That's 1s2, 2s2, 2p2 because it's on the second column. And then nitrogen would be the same, except it's 2p3, 2p4, 2p5, and then for neon, 2p6. Right? So for neon, it's 1s2, 2s2, 2p6. And then we can just keep going. For sodium, 1s2, 2s2, 2p6, 3s1 for sodium. And then for magnesium, it would be 3s2. And then 3p1, 3p2, p3, p4, 5, and 6. And then 4s1, 4s2. And then once you get to the D block, you have to subtract 1 from the row number, right? And that's why we have n-1 for the D block. So for scandium, that would be 4s2 and then 3d1. So the full electron configuration for scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d1. Okay, and we can do the same thing for titanium all the way to zinc. Okay, and then once you hit the p block, it goes back to np, right? So that would be 3d10 for zinc, and then goes back to 4. So 4p1 for gallium. Okay, and then once if you're dealing with one of these elements that involve the F block, you subtract 2 from the row number. So you can use this information to basically write out any electron configuration for any element in the periodic table. And you can also combine this technique with the noble gas electron configuration. So let's say that I want to write the electron configuration for neon, right, Ne. Or let's say I want to write the electron configuration for aluminum, and I want to use the noble gas electron configuration. So aluminum is right over here on the third row, And I'm going to use the preceding noble gas, the noble gas right before aluminum, which is neon, right? So the elements in the periodic table are arranged based on increasing atomic number. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. So the noble gas before aluminum is neon. And so to write the electron configuration for aluminum using noble gas electron configuration, we have neon and then 3s2, 3p1. Okay, so again, Ne, the symbol of Ne, and then 3s2 and then 3p1 for aluminum. And then we can do the same thing for, let's say, gallium, right? So the preceding noble gas is argon, and this is going to be our starting point. So argon followed by 4s2, 3d10, 4p1. All right, so let's look at a few more examples on the next slide here. So again, by knowing the orbital blocks, the n values, and the position of any element in the periodic table, one can easily write the electron configuration for any element. So again, we have the periodic table here, if that helps you out, or you should also have one on hand. So for practice, using the periodic table and orbital blocks, determine the electron configuration for these elements. So we have these elements here, lithium. All right, so lithium is right over here. So this is the S block, and it's on the second row. So to write the electron configuration for lithium, that would be 1s2. Okay, this is 1s1, 1s2, 2s1. So that's for lithium. 1s2, 2s1. All right, for nitrogen, we have nitrogen right over here, which is on the second row. So again, we're going to start off with 1s2, 2s2, 2p3 for nitrogen. So 1s2, 2s2, 2p3. For magnesium, magnesium is right over here on the third row in the S block. So we have 1s2, 2s2, 2p6, and 3s2 for magnesium. And then iron, we can probably just use noble gas electron configuration because it's all the way down here. We don't want to keep writing all the sublevels. And so we're going to start off with argon, the preceding noble gas. And then we know that iron is on the fourth row and in the D block. So for iron, it would be argon followed by 4s2 and then 3d, 1, 2, 3, 4, 5, 6, 3d6. So argon, 4s2, 3d6. Okay, so basically 4s2, 3d6, this part right here, is the electron configuration for argon. All right, and then we can do the same thing for germanium. Germanium is right over here. So it's also on the fourth row in the P block. So we can use argon as our noble gas. So argon, 4s2, 3d10, and then 4p2. Okay, so basically we have 3d10 and 4p2. So this is the electron configuration right here for, again, argon. And then uranium is all the way down here at the bottom. Wow. So this is row number 7 in the F block. So if we use a noble gas electron configuration, that would be radon right here, Rn. So we're going to use Rn followed by 7s2. And then this is actually the d orbitals right here. So you're going to have, this is the D block. So you're going to write down 6. That would be 6d1. So lanthanum and actinium are actually right over here. So they have a d orbital. Okay, so that would be radon, 7s2, 6d1, and then 5f3. So the arrangement of this part right here, the lanthanide and the actinides, the lanthanum and actinium, these two elements right here are actually inserted over here. Okay, so when you count the total number of elements here, there's actually 15 when there's supposed to be only 14, right? And the reason why is because the IUPAC, the organization that arranged the periodic table, decided to include the lanthanum and actinium along with the rest of these elements here because they have similar physical and chemical properties. All right, but I'm not going to ask you on the test something too massive, right? I'm not going to ask you to write out an electron configuration of one of the heaviest elements in the periodic table. And so just the simple ones. So in the beginning of the lecture regarding electron configurations, we talked about the Aufbau principle, which basically states that sublevels are occupied by electrons in increasing energy level. But some of the transition elements or transition metals, the metals in the middle of the periodic table, don't follow this rule to some extent. And so when you look at chromium, copper, these four elements right here, chromium, copper, niobium, and molybdenum, they actually don't follow the Aufbau principle. Okay, so for example, these are the expected electron configuration for these four elements if we follow the Aufbau principle. So you have argon followed by 4s2 and 3d1, right? So 4s2 comes first before 3d1 because 4s is lower in energy than 3d. But in reality, the actual electron configuration is shown on the right over here. So for chromium, for example, it's actually 4s1, 3d5. And the reason behind that is due to the energy level of the 3d sublevel. And remember that you have basically 5 different d orbitals, and so it's more stable to distribute the elements, or it's more stable if you distribute the electrons evenly on the 3d sublevel instead of completely filling up the 4s. All right, same thing with copper, niobium, and molybdenum. So instead of 4s2, 3d9 for copper, it's 4s1, 3d10. So for the next test, for the first test, make sure that you know at least the first two. You have to remember that chromium and copper are the two elements in the periodic table that don't follow the Aufbau principle, that they have a different electron configuration compared to the expected electron configuration. All right, so now the last thing that I want to talk about is electron configuration for ions. And if you remember, ions are basically atoms or elements with positive and negative charges. So if you have an ion with a positive charge, that's called a cation, and an ion with a negative charge is called an anion. And so let's say, for example, we have chlorine. What would a chloride ion, Cl minus, electron configuration look like? Okay, so for chlorine, a typical chlorine atom would have this electron configuration shown here. So I'm using the noble gas electron configuration. So you have neon, 3s2, and 3p5. So if you have a chloride ion, this tells you that you have one extra electron compared to a neutral chlorine. All right, so you have one extra electron. So how many electrons does chlorine have? It has 17 electrons, right? So a normal chlorine atom, a neutral chlorine atom, has a total of 17 electrons. Now, if you have a chloride ion, it means you have one extra electron. So 17 plus 1 is 18. So that means that a chloride ion should have a total of 18 electrons. And so whenever you're writing the electron configuration for chloride ion, all you have to do is add one electron to the highest sublevel, which in this case is 3p, right? So a chloride ion has this electron configuration. So 3s2, 3p6. We just added one electron to the 3p5. What about cations? So cations are ions with less number of electrons compared to the neutral atom. So let's say we have calcium versus calcium 2 plus. So positive 2 charge tells you that you have 2 less electrons compared to the neutral atom, compared to the neutral calcium. So a normal calcium has this specific electron configuration. So you have argon followed by 4s2, right? And so if we remove 2 electrons from a neutral calcium, we're removing this one, the 2 electrons here in the 4s. And so this becomes calcium 2 plus, argon, and then 4s 0, right? Because we subtracted 2 electrons from the 4s. And whenever you're writing the electron configuration for an ion, you don't have to really include 4s 0. So it's basically implied that the 4s is there, it's just empty. It doesn't have any electrons. So you can just report it as AR. So that means that this calcium 2 plus has the same electron configuration as the noble gas argon. So let's look at a few more examples here. So we have a nitride ion, aluminum ion, and a sodium ion. So a nitrogen, the element nitrogen, has a total of 7 electrons. So nitrogen has 7 electrons, and so since we have a negative 3 charge here, that means we're adding 3 electrons to 7. So we have a total of 10. So the electron configuration then looks something like this. So you have helium, 2s2, and 2p6 for a total of 10 electrons. And this is actually the same electron configuration for a neon, because now the number of electrons of nitrogen or nitride ion is the same as the number of electrons of a neon atom. Let's look at aluminum ion, Al3 plus. Aluminum, neutral aluminum, has 13 electrons. And so if you subtract 3, now you have 10 electrons. And so the electron configuration for an aluminum ion is actually the same as the electron configuration of a neon or even a nitride ion. See the similarity here? They have the same exact electron configuration. In fact, the third one here also has the same electron configuration as neon and the other 2 ions. And so when you have atoms or ions with the same number of electrons and the same number of electron configuration, these ions and atoms are said to be isoelectronic. Okay, so make sure that you remember this terminology. Isoelectronic. It means 2 atoms and ions have the same number of electronic configuration. Okay, so the same number of electrons, same number of electrons, and same electron configuration. That's what isoelectronic means.